Okay, so now I'm going to talk about the Ritz method, or the Rayleigh-Ritz method. This is on this talked about on page 170 and 175 of the textbook Chari. It's a pretty well-known method for solving problems that are there's not a good analytic solution. So you can use it to find analytic based solutions to complicated problems using approximations. So it's based on the variational principle that I just talked about, and you have to. It relies on trial functions. So there's somewhat of a little bit of guessing involved in trying to figure out what the best trial function is to try. So you basically try different functions and you put them into the integral equation to determine what gives the minimum energy. Let me talk about the details now. So it's based on the variational principle. It relies on trial. I think that's the wrong principle, isn't it? Relies on trial functions. Accuracy depends on choice of trial function. And the problem with this approach is that it's limited to homogeneous isotropic media. The reason is because the trial function, the function that you come up with is the complete solution to the whole problem region. So you can imagine if you have a really complicated problem, it's unlikely you would be able to come up with a function that would correctly describe the field all over the subdomain. But this is the precursor to, this is a good introduction to the finite element method, the beginnings of it. Limited to homogeneous isotropic media. Trial function defined over entire problem domain. And so it's a precursor to the FEA model, and can be useful for solving simple, intractable problems. So in order to explain this approach, I'm going to give an example, and we'll solve the problem. The somewhat disadvantage of solving the problem is that it's not, it's only going to have, it turns out it's only going to have one unknown variable. But if you have too many unknowns, it becomes, it's not manageable on a board. The textbook gives an example with two unknowns, but I'm going to give an example with one. So the example I'm going to give is to evaluate the capacitance. So consider a situation where we have two cylinders that are very thin, and then on the outside the whole circle has a voltage of 0, and then on this inner circle the voltage is V0. Okay, you may have seen this problem before in a textbook. So you can picture there's going to be, if you were to plot the electric fields, you'd see a gradient reduction, right? Because it would have the maximum here, and then it would decrease to 0 on the outside. So there is an analytic solution to the field, and so we're going to use that and compare it. So the question is, and so we assume that material is air, everywhere is air. So the relative permeability is 1, just to make life simple. So the question is, what is the capacitance? So the exact solution is capacitance is the charge over the difference in the voltage, and so the solution is 2 pi times the permittivity times the length divided by log B divided by A, where B and A are the radii as shown, and L is the length into the page. So our solution will be per unit length. So solution will be farads per meter. And so if you note, if we divided by 2 pi times the permittivity, then we'd be left with 3 geometric variables, but L will just assume is per unit length. So there's only 2. There's B and A. Okay, so that's the answer. So now we want to try to get this answer, but using the variational approach. Any questions? Okay, we'll see if we can do it before we leave. That might be a struggle. So, this would be a lot easier to solve if you used the textbook approach, but the purpose of this example is to give a way of solving problems that don't have an analytic solution, right? But this having the analytic solution allows us to check our approach. So let's say we can't figure out exact solution. So we do know that there's going to be a certain amount of energy contained in this system. So the energy is, if you look in the textbook, is going to be half times C V naught squared, and so then that can be rewritten as, in terms of the field, the electric field. So if we integrated the electric field all over the surface, that squared it and times it by the permittivity and divided by 2, we would get the energy. So, but we know that the electric field is related to the electric scalar potential of the by the gradient V. So then we could rewrite this as So this is then looking just like the functional that we finished, that equation 2 that we had, because we have the we have a del v squared. It was before we had del a squared, right? So this could be the functional, the basis for what we try to minimize to get the solution. So the functional for this problem can be written as if, so we can, so now let me write that out. So we need to evaluate this over the area actually we need to evaluate this over the area. So if we look at the problem, the field is only going to degrade along the radial direction. So we need to evaluate 2 pi r around it, and then we need to evaluate from a to b the integral in this donut shape, right? So therefore this can be rewritten, the surface area can be rewritten in terms of just a radius, because it's the field doesn't change as a function of angle. It's the same all the way around. It just decreases in the radius. So we can rewrite this as, and so the gradient of v is only going to have a change in the radial. It's not going to have a change in the angle. So we can simplify it down to del v del r squared 2 pi r dr, like that. And that's equation 12. So we want to minimize this. So the Rayleigh-Ritz approach involves trial functions. So the idea is that we have this functional, and then we try to find a voltage by using a trial function. And I'll put a hat on top of it for trial function. So we could have n unknowns in this trial function. So where C1, C2, C3 to Cn are n unknowns, unknown parameters. That we need to determine. And then R1, R2, R3, and so on are in trial functions. This n is not the same n as in the previous part. Are you okay with that? Maybe I could put that as M. Maybe I'll make that M for you. M. The unknown parameters. M unknown parameters. Okay. So the idea is, and I'm going to write out an example. I'm writing the general case here. So the idea is that if we substitute the trial function 13 into 12, the 12 was the functional down here that I've partly erased. If we substitute into 12, then and set the functional to 0 for the derivatives, for the derivative of each parameter. So we take the derivative of the functional and with respect to C1 and set that to 0. Take the derivative of the functional with respect to C2 and set that to 0, and so on. We would end up with M equations. The procedure will yield M simultaneous equations that can be solved. Solved to determine the trial function solution. The trial function solution. Okay, so it's a lot to take in. Okay, so off.
That the bottom of the functional for the problem can, and so as you from epsilon out of 2, integral from A to B, dB, extension ends there. Is that equation?
No, that's 12. Yeah, I just erased the. It's 2 pi. It's got the 2 pi r dr right on there. Yeah, that's this. Okay, so this is a lot to take in, but this I'm trying to explain things that are good on computer on the blackboard. So the trial function, what should that look like? So usually we could start with a polynomial. So often the trial function polynomial. We can think in polynomials. So then, okay, so for that capacitor problem that we started with, let's start by saying that, so let's guess the solution to the capacitor problem has trial function given by this here. So there's two unknowns, C1 and C2. Now it turns out though that in this case we have two boundary conditions, A and B. So we can actually, and given the boundary conditions, we can actually write this trial function with no unknowns, because we have two boundary conditions. So in the first case, when we write the trial function like this, we don't have to evaluate the derivatives in this equation. And it'll take a bit of thinking to realize what I mean, I think. But I'll work through it with this one first, and then we'll try a more complicated one where we have to take the derivative. And you will see that it gets pretty complicated pretty quickly. Okay, so in this case, I'm guessing, this is a guess, I'm guessing that this is the solution. It's got, so this equation needs to satisfy the boundary conditions. So in order to satisfy the boundary conditions, we have that at r equals a, we need it to equal v naught, and r equal b, we need it to equal 0. So therefore, we could try to write it. So let's try v is equal to v naught minus v naught b minus a times r minus a. Okay, so this was judiciously thought out. Okay, so now if we compare, so if we put in, we can check this, so if we put in a in here, then we'd get v naught. If we put in b in here, then we'll get 0. So that satisfies these two boundary conditions. Okay, so if we compare 15 to 14, then we can note what these terms are relative to this one. So this is the general statement of what the we have two unknowns, C1, C2, and two variables. But in this case, in order to satisfy these boundary conditions, the equation simplifies down to this one. And so if we compare 14 and 15, we can see that C1 would equal V naught, and R1 would equal 1, and then C2 would equal V naught over B minus A, and then R2 would equal R minus A. So that's that tries to give you an example of this is a general mathematical statement, and then this is a practical equation that satisfies the certain boundary conditions for this problem. And so in this case, you can see that we aren't, because we have two boundary conditions and we have two unknowns, C1 and C2, we can actually write out a voltage equation, the electric scalar equation, in terms of only B and A. Okay, we can now use this so this is actually the answer. But we need to now use this to check the the capacitance. Okay, so in order to do that, we need to go back to here, and you can see that the capacitance can be found by evaluating the right side here. Okay, so we're saying that this is our trial solution. So let's put that in to this equation here and figure out what the capacitance is. Okay, this is actually the physics part. Now we've got our trial solution. That's the mathematics part's finished. I mean, the optimization part. Well, it's not really optimization, but well, it is. It's the optimization for this using this trial solution. So let's put it into here and see what we get. Substitute the trial function 15 into 12. So this was 12. So we have that the derivative, the partial derivative of the trial function with respect to r, that's what we need to evaluate. So we take that and we square it. So the derivative is minus v naught b minus a. So we now, with that in mind, we put this into 12 and we get out v naught squared divided by b minus a squared 2 pi r dr. Okay, now we need to integrate that from b to a. And got that. So it's going to be, we can take the v naught out. So it's just going to be b minus a square. It's going to be they're going to be r squared b minus a. So it's just going to be r squared divided by 2, and then we substitute that in. B squared minus a squared divided by 2. Sorry, that 2 cancels there. That goes away. And so then we get, so this can be rearranged, the b minus a squared can be rearranged into b minus a and b plus a. So the b minus a's cancel, and so then we're left with b plus a divided by b minus a. So that's when we evaluate the functional, and now that has to be what we're hoping that this will be equal to half c v naught squared. So then this is the trial capacitance equation. So then the v naughts and the 2 cancel, and so we can rewrite this as thus c hat is equal to epsilon naught pi b plus a divided by b minus a. So that's what we have got out as our solution. So we could rewrite that in terms of just the geometric variables. missing a 2. Those 2's cancel. 2 plus 3. No, that should be b minus a. Yeah, I think that's right. So let's put in some values. So b and a.
What's that symbol of 2 pi epsilon?
Oh, C hat. That's the capacitance. That's the approximate capacitance. So we so if we put, I'm just going to run through these numbers. So if we put some different numbers into here, this is b over a. So we'll have 2, 4, 10, 100. That's the ratio. And so then this will be 1.5, 0.833, 0.612, 0.51, but and then the exact is this 1 over log b minus a, b over a. And so that gives 1.44, 0.721, 0.434, 0.217. So you can see that it starts to deviate significantly from the actual answer when the ratio b over a becomes large. So it starts to deviate significantly. So that's not too bad if it was b over a was just a ratio of 2. Okay, so one way to improve the accuracy now is to go back and choose a more complicated trial function. So let's now try a trial function that has an additional term. So let's now try a second order trial function. Okay, so in this case we have C1 plus C2 R2, actually I'll put the R1 there too, C2 R2 plus C3 R3 squared. Oh, sorry, no, there's no R1 there, silly. So we're trying a different trial function. It's going to have a squared to the power of 1 and then a coefficient here. Okay, so that's the form of the trial function. So now we look at our problem and we scratch our heads and we think about it for a while. We come up with an equation that matches the boundary conditions that we want to just try. Okay, so then the most general trial function that satisfies the boundary condition is Okay, and so this would be a judicious type of equation that you would determine. 1 plus C naught R minus A divided by B minus A minus 1 plus C naught times R minus A squared divided by B minus A squared, and that's 17. So now we've got the B and the A, and then we've got the one unknown. So in this equation, there's three. In the general equation, there's three unknowns. So you would. But because we have two boundary conditions, we can eliminate two of these unknowns because the boundary conditions have to satisfy two unknowns. So then we're only left with one unknown. And so in that case, this would be an example of an equation that would satisfy the boundary conditions and have one unknown. So for example, if we set R equal to A, so then this would be, these would all go away, and we just have the V naught. If we set R equal to B, then it becomes 0. If you look at that. Okay, so then this is where actually the Rayleigh-Ritz approach really comes in, because now we have a trial function that does have an unknown that we need to figure out. So what the Rayleigh-Ritz approach says is that we need to, and you're going to enjoy doing this, you need to substitute this in to the functional and take the gradient of this, and then solve the functional to figure out what the C naught is. Once you have the solution to C naught, then you can put this back in to the functional and calculate what the capacitance is. So there's two steps. First, we have to figure out what that C naught is to make the functional minimum, and then, because it's an application, we want to figure out what the capacitance is. And so we need to then, once we know the unknown, we need to substitute it back in to get the capacitance out. Okay? So I'll outline the approach, and then I'll let you do that for your homework. So we have C naught is an unknown constant. Okay. So we first have to take the based on the Rayleigh-Ritz approach, we have to take the gradient of this with respect to the unknown, but we also have to note that this has got a gradient of v in it. So let's first take this gradient of v. So we know that E is equal to minus gradient of v with respect to r in this example. So the gradient of this with respect to r, the partial derivative with respect to r, we can write out. So that is minus v naught c naught b minus a. And then the second term, you first take the derivative outside the brackets, and then you take the derivative inside the brackets. So we're left with 2 and then we add a minus here, so it becomes plus. So we have 1 plus c naught r minus a v naught divided by b minus a squared. Okay, so that's the derivative of v with respect to r. So now we need to substitute that back in. So substitute that this is 18, so we put that 18 back into 12. 18, and remember 12 is this one here with the dv dr r 2 pi dr. So now we substitute that back in. AB minus V naught C naught B minus A plus 2 1 plus C naught R minus A V naught divided by B minus A squared, and that's all squared 2 pi R dr. Okay, so then now that's the functional. Now you have to take the derivative of that and set it equal to 0. So differentiate with respect to C naught, and then integrate with respect to R. So, and then you set it equal to 0. Okay, so you solve this, and then you get out, and I'm going to give you the answer. So solve for C naught, and you get out that C naught is equal to minus 2b over A plus B. So this gives the minimum. Now I didn't prove that this is the minimum, not the maximum, because it's the derivative. It could be a maximum. So I'm trying to make this generally a practical class. So I'm not going to do any proofs and things like that, but you can read more about this if you want in the Rayleigh-Ritz method. So I'm trying to give an example here. So we take the gradient, and since it's 0, we're assuming it's the minimum, and you can read more about why that's the case. And so then this is the actual solution you get out. So now that's the C naught. So now then that gives us the answer to the unknown in the trial function. The trial function is 17. So we've figured out what C naught is. So that is now, we have now finished, since we've figured out what C naught is, we have now finished the Rayleigh-Ritz solution by evaluating this. But since I was trying to make this a practical problem, then we want to figure out what the capacitance is. So we need to put this back into here and then solve for C. So then I think I'll have to, I don't want to go over time, so I think I'll stop there, and we'll do that second part next time. Okay, thank you.